Hello, we are Group 2 and we are composed of Hugo Acosta, Selena Birch, Brianna Moreno, and Mark Rodriguez. Today we will explain one of the fundamental topics in systems engineering, testing. Following the VVT definition, testing is a subset of verification and validation dealing with actively operating the system and verifying it or validating it. We will also explore the two main parts in testing, white box system testing and black box system testing. The second part is further divided into basic testing, high volume testing, special testing, environment testing, and phase testing. We will also provide specific examples as to how these types of testing is accomplished based on the projects being developed by our fellow classmates. As mentioned before, testing is generally divided in two types, white box testing and black box testing. These terms describe the point of view a test engineer takes when designing the test process. White box testing is undertaken with an internal or a structural view, whereas black box testing is concerned with a functional or external view of the item being tested. Furthermore, white box testing is usually conducted at the unit or component level and tend to discover structural problems, and black box tests are usually conducted at the subsystem and system level and typically detect functional defects. Let's take a look at a type of white box testing, component coverage testing. The main purpose in hardware component testing is to verify that the largest possible portion of the system desired to be tested is covered by a set of individual tests. The goal here is to determine input test parameters or patterns that will trigger a fault in the system under test. Another goal of this type of testing is a high detection rate of real defects. Component coverage testing in hardware, on the other hand, refers to the process of verifying that a certain test sequence has been covered or tested all the components in a circuit or a system. Let's explore more about component coverage testing in hardware and how it can be applied in some of the other projects developed in this class. But first, let's address some characteristics of this particular type of white box testing. Given that the list of potential hardware defects in a system is very large, the approach commonly taken is based on creating fault models that identify a well-defined, manageable failure space of targets for the generation of test patterns analysis and validated by means of testing. These fault models identify fault characteristics such as variability, multiplicity, or effect on function and operating speed. Variability refers to non-permanent hardware faults that may appear on non-consistent basis or in relation to transient events within a circuit. Multiplicity refers to the multiple faults affecting the behavior of the unit under test in unexpected ways. Effect on function or operating speed refers to the faults that may affect the overall functional behavior of hardware. These faults usually only manifest after a specific sequence of inputs. Nowadays, there are different ways of generating and validating test patterns, sometimes called test vectors, either manually or automatically. Test pattern generators determine test vectors for a given fault model that will propagate a fault all the way to an observable output. In other words, these are called fault simulations. These simulations contain a definition of the hardware circuit under test, such as an analog or digital component, such as a logical gate, and they simulate the behavior of the system that is under both good and bad conditions. It is important to note that these simulations, though, often require a considerable amount of execution time and therefore are limited or restricted by the size of the circuit we want to test. Lastly, hardware test pattern generation techniques can be divided into the following categories: manual generation and pseudo-random generation. Manual generation is when test patterns may be generated manually by test engineers for functional verification. A model of the system should be simulated in order to verify the level of fault detection as well as to identify components whose failure has not been detected. Pseudo-random generation, on the other hand, is when test patterns are generated using a random number generator and then simulated at the circuit level. Usually, this technique is used early in the testing process to identify easy faults. An example of this type of white box testing can be observed in Groups 3 project, Autonomous Security Surveillance Tracking Drone. More specifically, during the validation and verification of requirement number 44. This requirement states that the system shall automatically increase speeds by 6 miles per hour when flying into high winds. Component coverage testing can be applied to test this particular requirement because a full model can be used to evaluate the variability in which the desired speeds are not obtained, or even if a multiplicity factor exists and a pattern exists which prevents the tracking drone of behaving as it's required. Another example of some of the techniques explained before is the validation and verification of requirement number 77 of the tracking drone system. This requirement states that the system shall have a breaker switch in the event of an emergency shutoff. Techniques such as manual generation or even pseudo-random generation can be utilized to inject a power shutdown and observe if a failure exists in the system's emergency breaker switch.
One type of white box testing is interface testing. The purpose of interface testing is to see how systems or components interact with each other. There are different categories of interactions among interfaces, including material, where there is a physical material exchange between interfaces; spatial, where forces are transferred between interfaces; energy, where there is an energy transfer, such as electricity; and information, where there is an information or signal exchange. Information is considered a very important test for complex systems. There are different classes considered for information testing, including hardware-hardware, hardware-software, software-software, and human system. There are two main phases to interface testing. The first phase is using dummy interfaces. These dummy elements represent the other interface being communicated to, without actually having an operational interface there. This provides more control over primary interface testing. The second phase is actually integrating and testing the two operational interfaces together, mimicking how these interfaces will interact in the real world. Now that we've had a slight introduction to interface testing, we must now go over some types of interface tests and examples. The first type of interface testing is hardware interface testing, which has some common interface layers to focus on, including physical level interfaces, which includes testing physical connections of two parts of a system; electrical level interfaces, which sees if an electrical signal produced by one component can be accepted by another; and protocol level, which tests internal structure and order of data flow through the interfaces. An example that includes all three of these interface hardware tests is Group 3's Autonomous Security Surveillance and Tracking Drone. The physical level testing can be done by checking the physical layout and wiring from the power subsystem to every other hardware subsystem on the drone, such as the propulsion system and the cameras. The electrical level testing can also be used for the power system to see if the electrical signal created by the power system is compatible with all of the other subsystems' power supplies. It was mentioned in Group 3's IVV plan that there is a need to have evenly distributed voltage among subsystems or the motherboard could malfunction, so this electrical test is necessary for the system. The protocol level test could be done for the sensors and the camera. It was mentioned in Group 3's IVV plan that the cameras depend on the sensors to recognize an emergency landing. One protocol test could be making sure that the sensors of the drone have the correct format output that will allow the camera to understand and initiate its emergency protocol procedures. This not only looks at the format of signals provided by the hardware, but it also looks at the data flow between the hardware systems to enact hardware emergency protocols. The second type of interface testing is software interface testing. This type of testing has some common types of interfaces to test at, including parameter interface, where calling and called elements agree on parameter protocol, and message passing interface, where calling and called elements agree on the nature of the message. An example that includes these two software interface tests is our own project, the glucose monitoring system. The parameter interface could be tested by our database and the mobile application. The app pulls a history of glucose measurement data logs from the database and uses that information to create visualizations and graphs to depict those glucose measurements. In this case, we would test to make sure that the app requests this information and the database agrees to give that information based on the protocols defined. These protocols include how much data to send the app, the order of the data, and the format of the data. The message passing interface we could test is our messaging system between the user and the physician. We could test a protocol for sending the emails to the doctor. The system must verify user access, must wait for user confirmation to send the email, must know what contents should be inside the email, and must know how to deliver the email, which is using encryption and other security measures. The last type of interface testing discussed is human system interface testing. This type of interface can be explained by our own glucose monitoring system. A test that can be done involves using diabetic patients to test the glucose measuring bracelet prototype in their daily lives. This takes into consideration the unpredictability of the user, because each user will measure their glucose according to their own requirements, go about their days in different environments, and all have different behaviors. This test will also consider system missions by testing if the readings and other useful information will be available through the prototype user interface, and whether users can operate the bracelet, like take measurements manually or automate them, in an appropriate way. It will also verify if the modern technology used in this product, which would be the biosensor, is appropriate for user consumption. Lastly, this test will determine if the ergonomics and operation of the bracelet is appropriate for users in their operational environment. So this test would cover all of the considerations needed in HSI testing. Along with the considerations, this test would also cover the HSI testing heuristics. The bracelet would be simple and natural, having minimal interactions with the user and operating in the user's preferred language. It would have a minimal user memory load, which would show that the user has complete control and freedom while using the device. And the bracelet would also provide handling user errors and offer possible solutions to those errors. Boundary value testing includes selecting test cases for a software or embedded system that are at the extremes of the product's operational values. This type of test finds a lot of errors in a system because it operates at the very ends of the system. However, it is not very thorough, so it cannot be used to validate a system. An example of this type of test could be used on Chuck Easton's secure implantable medical device. He even specified some boundary value testing within his test component document. A computer could be connected to the modified medical device, and the computer would send out commands to the device that exceed its preset boundary conditions by greater than 20% and less than 1%. So not only is he testing values that are slightly out of the boundary by 1%, but also values that are greatly outside of the boundary at 20%. This test would help prevent unauthorized users from changing the preset boundary conditions of the medical device.
Hello, this is Mark Rodriguez, and I'll be presenting two methods of black box testing from Chapter 5. 532, Decision Table Testing. Decision Table Testing method focuses on validating responses of a system under specified conditions and constraints. Rationale is system testing is accomplished by means of a decision table, which is a precise and compact way to model complicated logical behavior. Method is the construction of a decision table accomplished using the following steps. Step 1, identify all the possible conditions and their combinations that could affect the behavior of the system. Step 2, for each and every condition identified in the first step, define all the possible system actions in response to these conditions and their combinations. Decision tables are typically divided into 4 quadrants: conditions, condition alternatives, actions, and action entries. Each condition corresponds to variables whose values are listed in the condition alternatives. Each action is an operation performed by the system under the stated conditions. System for comparison. For this type of testing, I've selected Group Force project on the battery-operated washer and dryer system. Based on the group's requirements document, they describe conditions: washer usability, dryer usability, and battery usability, whereas condition alternatives could be defined in combinations that could affect the system behavior. Additionally, Group 4's project listed several actions: battery charging, user safety, maintainability, that can be performed by the system under stated conditions. Next, I'll be presenting 533 finite state machine testing. The purpose of finite state machine, or FSM, testing method is mostly to evaluate systems for proper execution of control functions. FSM modeling involves the concepts of system states, events, transitions, and activities. Engineered systems that embody FSM philosophy are characterized by a behavior pattern where, under each state or mode, the system behaves or performs activities and generates outputs in a specified and unique manner. The system remains in that state until a specific external input or internal event occurs. When that occurs, the certain conditions are fulfilled, the system transitions into another state under which it may perform an entirely different and unique set of tasks. Rationale is an FSM is a way of thinking about engineered systems and is used to model the dynamic behavior of complex systems. An FSM model has a finite number of states and transitions between those states, which occur in response to specific events within the system or inputs to the system. The state of the system represents a situation during system life when it performs some activities or waits for some event. More specifically, when the system is in a given state, it will perform specified activities associated with this state and usually produce specific outputs. A transition is a relationship between the two states, indicating that an entity in the first state will perform certain actions and enter the second state when a specified event occurs and specified conditions are satisfied. This is usually shown by a state machine diagram. Method. From a testing standpoint, a system may fail a test if it's exposed to an internal or external event. The guard conditions are appropriate and the system either does not transition to another state or transition to a wrong state. A system may also fail if it does not produce an expected output while in a given state. With an FSM model, test coverage criteria can be based on the structure of the state machine model. This includes testing based on state event combinations, transition structure, and paths specified by the state machine. Typical FSM testing strategies are as such: test for fault action, test for guard condition fault, test for an unspecified event or missing transition, test for illegal event failure, test for unintended event failure, test for state fault, test for next state fault, Test for extra transition. System for comparison. For this type of testing, I selected Group 1's project on patient delivery system. Based on the group's requirements document, they describe states that would require proper execution of control functions. By the description of the system requirements, an FSM would be suitable using different test strategies, such as test for fault and use for patient monitoring system, test for an unspecified event or missing transaction for the medical billing, and test for unintended event failure, which would test the electronic health records.
Human System Interface Testing, or HSI. The purpose of this testing method is to validate that the HSI is functioning properly from both the ergonomic and the functional point of view. HSI testing should consider both the input as well as the output boundaries between people, operators, and users of systems and the system itself. HSI deals with input devices, which are how humans control systems, and output devices, which are how humans interpret systems information. HSI performance determines how easily a user may control and comprehend underlying functions of a given system. HSI often is the part of the system that determines the acceptability of the system by end users. An excellent example of a HSI is Group 2's project, a glucose monitoring system. The top-level design of the glucose monitoring system consists of a glucose sensor made off of a photodiode, an infrared light emitting diode, instrumentation amplifier, and a microprocessor to calculate the levels of glucose in the blood. The IR light emits into the user's forearm. The photodiode captures the light. The instrumentation amplifier cleans and amplifies the obtained electrical signal. And finally, the microprocessor calculates a glucose measurement in mg/dl based on the amplified signal. In this case, the input would be the photodiode capturing the photons from the light, and the microprocessor would be the output as it calculates the sugar levels in the body. There are two components when testing HSIs. The first is the proper functioning of the interfaces. Testing HSI involves the process of evaluating user input into the system as well as the system output to ensure that the system satisfies the specified requirements. Testing must ensure that the system will not blindly accept any input that the user enters. Testing must verify whether the system's output is fully comprehensible to users having appropriate capability and training. The second component of testing HSIs is ergonomics of the interface activities. The objective of ergonomic design activities are to optimize the effectiveness with which work and other human activities are carried out, to maintain important human values such as health and safety, and to the extent possible, stimulate work interest and satisfaction. Testing for proper HSI ergonomic design will assure easily manipulated operator control interfaces and clear and intuitive representations of system conditions. This will decrease the probability of operator mistakes and misinterpretation of the system conditions. HSI ergonomic testing increases the likelihood of cost savings in operator training and knowledge retainment. A method of testing HSIs is through humans. The method of testing is using humans to input commands into the system and seeing how the system behaves. Human controls systems by issuing appropriate commands. The output of these systems stemming from these commands are then monitored. Monitors provide humans the information they need to control the system, provided that it is unambiguous and easily comprehended. Monitors take on a variety of forms, including computer screens, liquid crystal displays, and light-emitting diodes, printing on paper, and meter dials. The range of devices used for interfacing with systems are shown in Table 5.3. Test engineers must consider that each and every interface device connected to the system may introduce a certain problem, distinctive to the given device. For example, switches and buttons may typically introduce timing errors or wrong sequence phenomena. Keyboards may introduce text string errors, or a display may show incorrect information. Human input testing. Testing a human input interface or a human controlling a system, one must first validate that the system responds correctly to proper commands. Second, one must verify that the system recognizes, tolerates, and properly handles operator errors. Testing the input tolerant properties of systems by verifying the system is consistently able to detect and handle proper user inputs, detect user input errors, stop input errors from propagating beyond the HSI area, indicate the existence of input error to the user, provide some further suggestion about the nature of the input and how to correct the error, and permit the user to correct his or her error or to completely remove the erroneous input from the input interface. Validating suitable system response to improper user commands. Improper user commands include violate data type or size. An example of this is entering alphabetical characters in a numerical field and vice versa. Violate input restrictions. An example of this is unreasonably short or extremely long information in a name field or illegal values in a date-time field. Attempting to skip mandatory fields in an input form. Inundate system. An example of this is pressing a key in a keyboard or button for a long time. And last, activating input switches in an unexpected sequence or in a random manner. The following strategies may be used by a system to check for illegal human commands. Real-time validation. After each keystroke, mouse interaction, or switch activation, the system checks to see whether the input meets expected value or event. Otherwise, the system issues an exception. Committed value validation. After the user has filled out a given field completely and commits his entry by pressing a key or to move on to the next field, the system checks whether the entire input field meets the expected values. Otherwise, the system issues an exception. And last, pass-through validation. After the user has filled out an entire form and commits his entry by pressing a carriage return key, the system checks all the fields in the form at once and issues an exception for the invalid fields. Validating HSI outputs, or human monitoring a system, involves generating and executing test sequences intended, first, to verify the system meets its specifications, and second, that humans react properly to the output information. Figure 5.11 shows an example of an abbreviated flight plan form for which the following must be functionally verified. Test box. This field is available for the free text insertion. Virtually always, there are limitations on the allowable number of characters and permitted set of characters. Selection box. All relevant destinations are available for selection in the destination field. Radio box. There are only two possible types of flights available, scheduled and unscheduled, and only one type of flight can be selected and depicted in the flight field. Checkbox. There are two possible types of payload available, passengers and cargo, and either one or both may be selected as depicted in the payload field. Buttons. Pressing the Enter button will activate the flight plan, and pressing the Cancel button will terminate the request without activating the flight plan. Also, the following tests must be done to validate the suitable system output to improper user inputs. Inundate system. Violate data type or size. Violate user input restrictions. And lastly, skip mandatory fields. These were covered in the previous slide, so please reference that slide for explanation. Overall, we covered white box testing, which focuses on the internal or structural view of systems, and black box testing, which focuses on the functional or external view of the item being tested. And we covered the testing components of black and white box testing, which are component coverage testing, interface testing, decision table testing, finite state machine testing, and human system interface testing. In addition, we included examples that included projects from class so that students can relate the information to a system they know to gather full understanding of the testing methods.